The second part of this chapter on water involves looking at water treatment. Now, there are two phases to this water treatment. Water is treated before it comes to the home, and water is treated after it leaves the home. So I prefer to call them water treatment and sewage treatment. So just not to confuse the two. The first part we already have done in junior cert. Most of us looked at water from a very kind of basic point of view, but the major steps were explained to you at junior cert biology level, or maybe junior cert chemistry. And we're just going to fly through them again. You'll notice down at the very bottom down here, there's a link. You can look at that in your own time. That link down here, that'll show you a kind of a video that has maybe more information than you need in terms of water treatment, but it's a nice visual to be able to see exactly what we're talking about in terms of the paragraphs and words and sentences that are going to come up on the screen in a few moments. So what are the major statements? Where does water come from? It comes from lakes, it comes from rivers, it comes from reservoirs, and it has to be brought from there to our homes. But in order to make it a drinkable resource, it has to be treated. The water has to be safe. So therefore, they're not just going to simply pump from the sea to your house, or from the reservoir to your house, or from the river to your house. There's a number of stages that they need to look at to make sure that the water they discharge to your house is water that is healthy and water that is safe. So the first stage in this process is when it's brought in. Obviously, water coming in from rivers or coming from lakes or coming from the sea, it'll have large organic matter like twigs or branches or leaves or even dead fish, etc., etc. So they have to be taken out, and that process is called screening. So they pass through large wire meshes like a grill, and as the water rushes through, the large debris is removed, plastic bags, etc., etc., things that get into the water supply, like rubbish, which shouldn't be there in the first place, but it is. They get removed at this stage, and then the water that flows on is brought into what we call a settling and a flocculation stage. So they're brought into these big tanks. And at this stage, the water is very cloudy because there are particles suspended in there that don't dissolve in the water, and they have to be removed. Now, if they're heavy enough, they'll naturally fall to the bottom and form a layer of sludge. But there will be those particles in there that are too light to float, first of all, too light to sink, I should say, and too heavy to float. So they'll suspend themselves. They'll stay there. So the water will be permanently cloudy. In order to combat this, we have to get those particles that are suspended to come together and to flocculate, just like a flock of birds. They come together into a little piece of material that is heavy enough then to fall to the bottom. And in order to allow that to happen, we add in a flocculating agent, which we call aluminium sulfate. And aluminium sulfate, what it basically does is it cancels the charges around the flock, the little tiny particles that are in suspension, that normally keeps them away from each other. It cancels those charges, and it allows them then to come together into bigger particles, which eventually get heavy enough to fall to the bottom as sludge. And that sludge then is taken away. So at this stage, your water is clear. So it looks as if it's drinkable. It then has to be filtered because there could be things in there that are invisible to the naked eye. So we bring it into large tanks of sand and gravel. And the layers of sand and gravel get smaller and smaller and smaller as we get to the bottom, so that when the water passes through, anything then that is undissolved but too small to see basically runs out of space, and it gets stuck between the sand particles. So what comes out of the sand at this stage is water that is perfectly free of suspended material, water that looks good enough to drink. But there is things in there, like for example bacteria, which can cause danger to human health. They have to be removed. There may be things in there also that like chemicals and so on that have to be removed, but also we've got to make sure that the pH of the water is correct, and we have to make sure that it's good enough to use from a human health point of view. They add in a little bit of fluorine for healthy bones and healthy teeth. It's part of the water treatment process, and then once all that's done, we get it to our house. So after filtration then, when the water has passed through the layers of sand and gravel, and just remember, they are in decreasing order of size. The large particles, gravel at the top, then down to very fine sand at the bottom. And as the water percolates through, anything that is undissolved in that water will get stuck between the sand particles, and the water itself will pass through. In order to get rid of the bacteria, we add in a disinfectant. Now, all disinfectants are based on chlorine, or chlorine molecules, some type of chloride molecules or chloride salts. But we add in chlorine in order to kill the bacteria. And the nice thing about chlorine is that it remains in the water. So as the water travels, if bacteria were to re-enter the water, again, they wouldn't be able to survive because of the presence of chlorine. So the chlorine is there on a permanent basis to make sure that water remains bacteria free. And finally then, for our good health, they add in some fluoride salts. And the fluoride, same as in your toothpaste, for exactly the same reason, it builds up strong teeth and bones for those who drink it. So the very final step then will be, just before they let it go into your house, they've got to make sure that the pH is correct. So they have to make sure that it's not base enough that it could actually burn, or that it's not acidic where it could actually erode the pipes. So if it's too strong a base, they will add in some sulfuric acid, very, very small amount. If it's too acidic, they'll add in some lime, and they simply treat the water just before it gets to your home with these chemicals in order to make sure that the pH is just slightly above 7, maybe 7.7 or something like that, but slightly on the alkaline side. So they're all the stages that we go through before the water comes from the river or from the reservoir to your particular home. And as I said already, there's a video down here. You can press that. It's on the slides. You can have a look at that yourselves. And it's a little bit more informational. It's a nice diagram, nice film, shows you how the water rushes through. There's stuff in there that's not on our course. What you see on this slide here, that is what you will be asked on. Okay, so when our water is being tested, water has to be tested continuously to make sure that its quality is okay. There are two things they have to look for. First of all, they have to look for what are the total undissolved solids that are present in a body of water, and then they've got to try and figure out, well, what's the total concentration of dissolved solids? And this is actually a practical that they can examine at Leaving Cert level. So we're just going to run through it quickly. The undissolved ones are very, very simple. You take a certain known volume of water, say 100 centimeters cubed, and you weigh a piece of filter paper. Okay, so you get out the weight of the filter paper first of all. You then pour the 100 centimeters cubed of water through the filter paper, allow the filter paper to dry, reweigh the filter paper, subtract the weight of the filter paper before filtration from the weight of the filter paper after filtration, and the difference between the two, if it's even so slight, will be the total amount of solids, undissolved solids, in that 100 centimeters cubed. Now just remember, we want parts per million, and if you can remember what parts per million are, they are milligrams per litre. So if I have, say, 0.02 grams in 100 centimeters cubed, well then obviously that means that I'm going to go from 100 to 1000, it'll be 0.2 grams in 1000 centimeters cubed, which means then if I multiply that, because I want this in milligrams, by 1000, that would be 200 parts per million. So that's how we work out the ppms for that one. Now I'm going to go through a calculation with you in a few moments, so let's just carry on in relation to the procedure. So as we said already, you'll get your mass of a piece of filter paper, you'll record that, you will then pour a known volume, usually 100 centimeters cubed or 250, something that's easy to bring up to a litre. You will then allow it to dry and you'll reweigh, and then you will subtract W1 from W2, which will give you the mass of solids in that particular volume. And then you adjust the volume up to a litre, you change the grams to milligrams, and that is your ppm. Okay. What about the dissolved material? Well, to calculate the concentration of parts per million in dissolved material, or dissolved material in water I should say, we do the evaporation process. So again, you weigh an empty beaker, you add in a known volume of the water under test, you allow the water to evaporate completely, so the beaker is evaporated to dryness. You then reweigh that beaker, and the difference between W2, the beaker after evaporation, and the beaker before evaporation will be the amount of dissolved material that is present in that particular volume of water. And again, you adjust the ppm. So just to get this into our heads, when we're looking for undissolved, we use filter paper. Weigh the filter paper, pass the water through, let it dry, reweigh, subtract, and that's the amount of undissolved material in that body of water. If we're looking for dissolved material, weigh a beaker, put in a certain amount of water, let it evaporate, reweigh the beaker, subtract the two masses, and that will be the dissolved material present in that particular body of water. So just to go through that with you, weigh a clean dry beaker, then you put in again a known volume. It's always going to be a known volume because we have to adjust it up to a litre. So therefore we have to make sure that it's easy to adjust to a litre. So 100, 250, perfect. You heat the beaker to dryness, and don't scald it, don't burn it, because you might burn some of the material in there. So usually let it dry out slowly enough. Put it into an oven at maybe 150 degrees, or put it into an autoclave, or put it into somewhere that's nice and warm. Just leave it on the radiator, let it do it over 2 days. And then when it has heated to dryness, you reweigh, then you subtract the two masses, and then you adjust to ppm in the same way. Now we have a question that's coming up here, so I'm going to go through this with you. This is an exam question from previous years. When 1,200 centimeters cubed of swimming pool water, so again, just make sure when you're reading these questions, you know, I just love to highlight these things. So 1,200 centimeters cubed of swimming pool water was filtered. The mass of the filter paper upon drying had increased by 0.78 grams. When 250 centimeters cubed of filtered water has evaporated dryness, the mass of the residue obtained was 0.32 grams. Calculate the concentration of parts per million of suspended solids and of dissolved solids. Okay, well, let's just go through that. Now, 1,200 of swimming pool water was filtered. So you take 1,200 centimeters cubed and you filter it. Okay, the mass of the filtered paper upon drying had increased by 0.78 grams. So we don't need to know the mass of the filter paper. They're telling us what the difference was before and after passing the water through, so that's fine. So therefore, in 1,200 centimeters cubed of water, after filtering, we discovered that there's 0.78 grams of undissolved material, because it got caught by the filter paper. So this is the undissolved material. Now, we want parts per million, so we want to go down to a litre. Let's go to grams per litre. So that means we're going to go to 1,000 centimeters cubed, and therefore a very quick calculation, it'll be 0.78. So 0.78 multiplied by 1,000 and then divided by 1,200, and that will give me 0.65. So not 0.65 grams in a litre. So now what do we have to do? Go to milligrams. So you're going to multiply that by 1,000 to go to milligrams, and that will give me 650 milligrams per litre, which is better known as 650 parts per million. Okay, what about the rest? Part 2. When 250 centimeters cubed of the filtered water was evaporated to dryness. Now notice it's filtered, so the water coming through now should only contain dissolved material. Okay, so this one here is the undissolved, and then we're going to look at the dissolved. Okay, so when 250 centimeters cubed of the filtered water, that means that all the undissolved stuff has been taken away, so dissolved stuff is left, and evaporated to dryness, the mass of the residue was 0.32 grams. Okay, so there's everything we need. You bring this up to 1 litre, that's multiplying by 4, that's 1.28 if I've done that correctly. 4 2s are 8, 4 3s are 12. So therefore, if we want to go to milligrams, we multiply by 1,000, and that will give me 1280 milligrams per litre, which is better known as 1280 ppm. So calculate the concentration of ppm of suspended solids. Now suspended is undissolved, so that's 650, and dissolved solids 1280 parts per million. And that's it. Questions are as easy as that when it comes to that type of calculation. Okay, next question. Question 7 for a previous year. Explain how hard water is caused and how it wastes soap. Now, this is going back to what we did in the previous class. Hard water is caused, as we already know, by calcium or magnesium ions. That's all you've got to remember. How does it waste soap? It wastes soap because when you add soap in here, the first job that soap has to do before it can give you bubbles is it has to tackle these and has to remove them all. And once it has removed all of them, only then will soap give you what's called poshly a lather. I prefer to say bubbles, they say lather. Anyway, how can hard water be softened by ion exchange so that it is suitable for use as deionized? Now that's extremely important, deionized water. So therefore no ions whatsoever. And in that case, we have to use the resin that contains both H plus ions and OH ions. So just very quickly to go down here, we have a resin that contains H plus, and we've got another resin that contains OH minus. Now, the H plus is what will swap for the calciums. So one calcium in here, that would release two H pluses, because remember the number of charges in has to be the same as the number of charges out. And then over here, the SO4, the sulfate, or the hydrogen carbonate, whatever you want to use yourself, that will stick to the resin and that will release two OH minuses. And then obviously these two together will form 2H2O, which means there are no ions left in that body of water. Part B. In water treatment, what is the purpose of adding each of the following? A flocculating agent. Just remember what flock is. Think of the birds, little birdies like that, little birds all flock together. Yeah, it pulls things together. But it says, what is the purpose of adding each of the following? A flocculating agent. Well, it takes the tiny particles that are undissolved but in suspension. So they're too light to fall into the bottom. They're too heavy to go to the top. So they kind of float in the middle. They suspend themselves. What the flocculating agent does is it cancels the charges between the particles that are suspended to allow them to come together into larger particles, which then fall to the bottom as sludge and are taken away. Part 2. What's the purpose of chlorine? Chlorine is a disinfectant. It destroys the bacteria, gets rid of all pathogens. Number 3. Why do we add a fluoride containing compound? For good and healthy teeth and bones. Why do we add calcium hydroxide? Well, that's a base, so that would bring up the pH slightly over 7 to about 7.7, just to make sure, I suppose, the water isn't too acidic. And lastly, why might we add sulfuric acid? Well, for the other reason, in case the water is too basic and we have to bring the pH down. State the problem that would arise when each of any two of these substances is added in excessive quantities. Now, the two that are really easy to do here, chlorine. Chlorine is toxic to the human body. So therefore, if we have too much chlorine in a system, we're going to suffer. Simple as that. So they have to be very, very careful that the amount of chlorine we put in is not dangerous to human health. If you have swam in a swimming pool before, where they use a lot of chlorine, because a lot of people use the water, your eyes sometimes burn. Now that is bordering on chlorine. That might be just doing a little bit of damage to the surface, the mucous membranes of your eye. But anyway, it's still safe enough for us to swim in. The other one then you could say would be, why not too much sulfuric acid? Well, it's too acidic. It'll burn your mouth. It'll damage your teeth, because acid and enamel are great enemies. Sulfuric acid, any acid, always damages enamel. And then why not too much calcium hydroxide? It's too basic, and again, it could do damage to the inside of your mouth. Okay, part C. Why is water pollution by heavy metal ions, e.g. H2 plus or Pb2 plus, a cause of concern? Well, Hg, mercury. Pb, lead. Why are these of concern? I think you can understand why. Mercury and lead, they are toxic to the human body. They're toxic substances. And levels of these things, when they're very, very low, don't cause the human body any major damage. But when they get to a certain level, a threshold level, and they pass that threshold level, then the body begins to react to their presence in a very negative way. Name an instrumental technique that could be used to detect and measure the concentration of heavy metal ion in a water sample. Go back to fifth year. The mass spectrometer. Yeah, you could also say, if you wanted to, you could say to detect them, the flame test. But I think in order to try and figure out their detection and their measure, you would have to use what we would call the spectrometer, the mass spectrometer. Which you, if you're not too sure what that is, go back over it. Okay, and lastly then, explain how Hg, mercury, and lead can be removed from water supply. Now I'm going to come on to this in the next one. That's at the end of the next one when we talk about the sewage treatment. But normally, to get rid of these, what we would call heavy metal ions. These are heavy metal, not the music, which is rubbish. Apologies to all you metalheads out there. Can never understand it, just can't hear what they're saying. Don't know, they shout and scream and don't speak English. But anyway, there you go. Hg and Pb, heavy metal ions. The quickest way to get rid of heavy metal ions is simply to precipitate them. Now, you don't have to know, you're very lucky, you don't have to know the chemistry behind it. All you've got to know is that they are removed by what we call precipitation, T-A-T-I-O-N, reactions. So if we want to get rid of Hg2+, and we want to get rid of Pb2+, what do? We bring about chemical reactions that will precipitate them down to the bottom where they be collected and removed. Okay, so a nice question there on water treatment. Don't worry about part C, we haven't really touched on that yet, but we're about to do that now, going into sewage treatment. Okay, so if the last stage, just before it gets to the house, and we have one of these in the lab, which I'll show you if we, please God, get back before the exams, but it's a pH meter, and all it does really is, it's a probe that you put into a body of water, and when you put it into a body of water like that, up here, it'll give you the pH as a digital display. So quite an easy thing. Instead of having to use universal indicator or anything like that, you can use a pH meter. And I'm showing you this because there have been questions in the past that have said, what could you use to show the pH of a liquid? The easiest one to use is the technology of the pH meter. So, sewage treatment. Now, sewage treatment is the treatment of water after use. Water that has gone down the sink in the kitchen, water that has come out of the shower, water that's gone down the toilets, water that's gone down the sinks that you wash your hand in. Any water that we have used that passes through the pipes going out of our house is called sewage water. And again, there are a number of steps in sewage treatment which you can see here, kind of similar to water treatment before it comes to the house. So when it leaves your house, the first thing you'll notice is that there are screens. Yeah. So again, we've got the primary treatment. Now, sewage treatment is broken up into three things: primary, secondary, I'll talk about that in a moment, and then we have tertiary. Okay, the primary, which is the first phase, is all mechanical, which means the water is scraped by large grids or large filters, by metal filters, you can see them there, in order to remove any large debris, like baby wipes. People always flush baby wipes down the toilet, or I don't know why, because they get stuck, so they would be removed here. So things like baby wipes, etc., large debris that would be screened at this stage. And then the same as before, they're allowed into tanks where we have again flocculation. So with these flocculation tanks now, we allow stuff to fall to the bottom, which we would call again sludge, before we move them over into what we call settling tanks. Now in a settling tank, the small tiny particles that can fall to the bottom will fall to the bottom, and they'll be taken away as sludge. Okay. Then the water moves into what we call the secondary phase. So all of this here, by the way, that's all your primary phase. So screening for large debris, settling, filtration, and then the removal of the sludge. That's all the primary stage of water treatment, or of sewage treatment. The secondary phase is what we call the chemical phase. Oh, sorry, biological phase. Just get rid of that there. So it's the biological phase. Okay, and what happens now is that when the water has passed through screening, settling, and flocculation, it then goes into tanks where oxygen gas is bubbled through it to help the aerobic bacteria to digest any remaining sewage that might be present. So this is a decomposition phase where the aerobic bacteria are given plenty of O2, and by being given the plenty of O2, they are fed, they're activated, and they go to town, decomposing and digesting any remaining sewage that is present in this particular water. And you can see that it's moved quite well, it's agitated quite well to keep the oxygen levels high, so that the aerobic bacteria can do what they have to do in decomposing the sewage that is present. Okay, so at this stage now, and this is before the water is released back into nature, the last phase is where we have to look at the chemicals. That's where we call it the tertiary phase, or the chemical phase. And this is where we said a few moments ago, things like mercury are removed, things like lead are removed, but also things that like nitrates and phosphates, because nitrates and phosphates come from our washing machines, our dishwashers. Anything into which you put a detergent or a tablet will be very rich in nitrates, NO3, and PO4 phosphates. So all of these have to be removed. And as I said to you before, the quickest way to remove them is by what we call precipitation reactions. So we basically put in chemicals at this stage here in the tertiary process, which will remove the lead if there's any, or the mercury if there's any, but especially the nitrates and the phosphates. Because as we're going to find out in the next section, if they were to escape in here, if we were to get nitrates and phosphates in here, we would be feeding the naturally occurring algae, and they would think it's Christmas, and they would have a feast, and they would grow, and they would multiply rapidly, which means the water here then would become covered with algae, and the light would be cut off from plants at the bottom, stopping photosynthesis. But more about that later on. So in sewage treatment, 3 different phases. The primary stage, which is mechanical, screening, settling, etc. Okay, and then you allow the particles, so flocculation. Then we have the secondary phase, which is biological, where we aerate the water, allow the aerobic bacteria to decompose any sewage that is present here. Then we have the tertiary phase, which is purely chemical, into which we add chemicals to remove any mercury, any lead, but especially nitrates and phosphates, because they cause damage to life in the natural water supply. So just very quickly to compare and contrast the two. Water treatment, from where? From a natural resource into a treatment factory, where? To our home. Okay, this one here, from a home to a treatment factory, where? Back to nature. So back into your rivers or your streams, and that's why we've got to make sure that we treat water before we allow it back into nature, so that the water that we have used and we're now releasing back into the natural process doesn't do any damage to the organisms living in the water, be they plant or animal. Okay, if you click on that picture, now this is on your slides, if you click on that picture you'll get a larger version, you'll be able to read all the various different bits, but you could be asked to compare and contrast the water treatment process, that's treating water before it comes to the house, and the wastewater or the sewage treatment, which is water that is treated after it leaves our house and before it goes back to nature. So I'm going to leave it there, but what I am going to do is I'm going to put a set of questions up on Google Classroom that will accompany this video lecture, and I want you to work on those over the weekend. And again, if there's any difficulties with those, you may come back to me on Monday, and on Monday hopefully we'll finish off this chapter by talking about the biochemical oxygen demand. In other words, what happens if we do release nitrates or phosphates, and the titration that is behind that. And that will be that chapter finished. And then I'll give you a quick test on that chapter just to make sure that you have got the main points. And from there then we'll carry on to the options. So this will be the last part of what we would call core material before we get into the options, which will be the electronics and the crystals and materials technology.